Hello, this is Charlene. In this video, we're going to be talking about applications of quadratic functions. So I kind of want to look at parabolas before we actually get into the quadratic functions themselves. And let's talk about this for a minute. So when an object is thrown or projected from a starting point, we can approximate its path based on the shape of a parabola. And that's what these shapes are. These it starts at the bottom and goes up, it peaks, it comes back down. All three of these. There's kind of a tall one. Here's kind of one that's kind of flattened out here. And here's one that's kind of in the middle, medium size. But these shapes are called parabolas, but we also sometimes refer to them as parabolic shapes. So let's think about this in terms of real life. Let's say that this point right here, that's a cliff. And down here is the ocean. Here's the ocean down here. And so we've got this guy, he's sitting up here because he wants to jump off the cliff and dive into the ocean. Well, the path that he is going to take into the ocean is going to follow this kind of path. He's going to kind of jump off. He'll come to kind of a peak right here. There'll be a high point. It'll be the peak. And the peak of his dive will be at the top of this path. And so that peak is also what we would call the maximum height. It's like how high or what is the distance from the ocean is he when he is diving off. So it's kind of a maximum height. And I can't spell maximum height. Height. Okay. So, and that's that idea of him jumping off the side of a cliff. So he's starting way up here, but he's going to dive. He's going to kind of go up a little bit. He'll have a peak height. We'll call that the maximum height. And then he's going to dive all the way down into the ocean. And this is where he will hit the ocean. Okay. So this one over here, we could think of this like somebody who's going to throw a football. And he's not really high off the ground like a cliff, but his arm is not right on the ground, right? His arm may be at around 4 feet off the ground, 4 or 5 feet, where his arm throws and lets go of the football. So the football may leave his arm about right here, and then it'll kind of sail across the football field, and maybe another football player will catch it over here, or it may hit the ground at this point. So, but it still will have a maximum peak. It'll have a maximum height that it will hit in the air before it starts coming back down to the ground. This one right here, I kind of think about this one as being like, it's like, we're going to pretend like that looks like a golf club. Oop, that is not what I wanted to happen. Does that look like a golf club? Probably not, but maybe. Okay, so that's a golf club, and we're going to hit a golf ball. And the golf ball is going to take this path through the air before it comes back down to the ground as well. But this golf ball will be on the ground. It'll start right at the ground. And then it will have right here, it will hit a height that is the highest point, and we'll call that the maximum height of that. But this is what happens in real life. It's like if we jump off a cliff, if we throw a football, if we hit a golf ball, the object will follow a curved path. These are just some of the real life ways that you can think about these parabolic shapes. And it is going to be important going forward to put together this idea of how these real life situations and mathematical concepts come together. Now we're going to talk about quadratic functions and how they relate to these shapes. And as we said before, these shapes are called parabolas or parabolic curves. So the mathematical equation for a quadratic function, the parent one is the y equals x squared. That's how we know that an equation is a quadratic function, is that it will always have a squared term, a variable to the second power. Now this particular one right here is the parent function, y equals x squared, and it tends to it just graphs like a happy U. It just looks like a happy smiley face, and it typically will be, graphed like this. Like that's 0, 0. That's where that will be graphed. this graph right here will be at 0, 0. That's what the coordinates of this point are. But we can also write it as f of x is equal to x squared, because the y value is interchangeable with the function value, because the y value is the function value. Okay, we can also write this f of x is equal to negative x squared. This is what I want to point out, is that a negative x squared, well, it flips upside down. It flips upside down, and it is kind of what would we call an unhappy parabola. So all of these real life situations that we've talked about require us to have a negative exponent or negative coefficient in front of our leading x squared term. So all of them will be in this format. They will be unhappy. Something leaving someone's hand, a golf ball being hit, will all start at the bottom and go up. So it will always be an unhappy parabola. Okay, going forward, we're looking at some parabolas like this, and they will always have that negative. That means that we are talking about the parabolas in the shape. But I also want to talk about the other parts of a parabola when we graph them on the x and y coordinate. Whatever points are here and here on the x-axis, those points will be called x-intercepts. In different contexts, we call them different things. That we can call them x-intercepts. We can also call them zeros, because the coordinates of that will always have a y value equal to 0. It's like the y value is the function value. And at that point right there, like let's just say that that was like 1, 2, 3, 4, 5. That would be 5 on the x-axis, but the y value would be equal to 0. Okay, so that's the reason why we can call these x-intercepts. We can call them zeros. They're the solutions to the quadratic function if they are on that x-axis. So here is our x-axis, and any points that are on where the graph is crossing the x-axis, those are the x-intercepts, the zeros, the solutions. And this goes for all of these. It's like right there where that's crossing what would be the x-axis, that right there will be considered a zero or an x-intercept. Okay, so we also have in our quadratics, when we graph them, we have what I call the tippy top of that parabola. And, in the real life context, we call that the maximum height or the maximum point of that curve where that ball was following the path. But in math language, we're going to call that point the vertex. We're going to call it the vertex. So that means that our math vertex is going to help us find our real life maximum. Okay, so let's say that that point right there is equal to, if this is a 5 right down here, let's say that this is 1, right? We could say that that's 1, so 1, and then this up here, this might be 10. We don't know what it is. We're just taking a guess. So be 1, 10. But as that ball or whatever that object is passing, the x-intercept is going to tell us how much time is going by. How much time is going by. So the x-axis almost always houses the time numbers. So that means that over here, all of these numbers would be how high it is, right? How high it is. And so we would call this the y value, because that's going to be the y-axis. But if it's talking about how high it is, we can call it the height function. Yeah, we can call it the height function. So the thing is, though, that means that in our vertex, if our vertex is 110, well, the 1 is an x value, the 10 is a y value. Well, our y value is the function value about how high it is, so it's the height function. So the y value is going to tell you how high your object is going, and the x value down here is going to tell you how much time is passing. So much time is going to go by, and as the time goes by, the object is going to be at a different height depending upon the time. But that's going to help us with that. Like I said, this right here is going to be in real life, it's a maximum height. How high is the object? But um, in math language, that point is going to be what we're going to call the vertex. And that vertex is going to tell us how much time is going by, and then how high or the height of that object. So we're going to relate these. It's like in real life, we've got this object flying, and we're going to be able to tell how high our object is and at what time it got to that height. So hopefully this just kind of helps you start understanding how the real life situations are related to the math. This page right here is about the math understanding of quadratic functions and how it relates to these parabolic shapes. Okay, let's get started talking about applications of quadratic functions. Our problem here says at the end of his career, Sherlock Holmes retired to a small farm in the country and took up a hobby of beekeeping. Being of an analytical mind, he could not just watch a bee fly from flower to flower. He formulated a mathematical model for the parabolic path the bee follows from flower A to flower B. Says the height of the bee in inches is given by the function f of x is equal to negative 0.03 x squared plus 1.8x minus 24, where x is the distance in inches along the ground from Sherlock. Okay, and then we also have this little picture to go with it. I guess here is Sherlock, and here's the bee, and the bee is like traveling from one flower to another flower. And they've got obviously a parabolic curve here. Now, unfortunately, I have to give you a disclaimer because in real life, everybody knows that Sherlock Holmes is a fictional character, right? He was a famous detective, and the stories of Sherlock Holmes. He was a famous detective, but he's a fictional character. He's not a real person. But my disclaimer is that bees do not fly in a simple parabolic path like a thrown ball. While they can fly in remarkably straight lines while traveling, their flight is generally characterized by complex, agile, and often erratic patterns, including straight lines between flowers, hovering and zigzagging to avoid obstacles, navigate turbulence, or locate scents. But for the purposes of this problem, we are going to pretend that this is a real thing. Because we could still answer the questions based on the premise that we think that the bees are following a parabolic path. So that's what we're going to do. We're going to just kind of go with it. Okay, the first question they ask us is, what is the maximum height that the bee reaches as it flies from flower A to flower B? And of course, this is with respect to this function that Sherlock came up with. This function, this quadratic, describes this curved parabolic line or path that the bee is following. Okay, they want the maximum height. And if you remember, the maximum height is going to be here at the top of this curve. So that's going to be the maximum height. And in math language, that's going to be our vertex. That point at the top, the peak, is going to be the vertex. So the vertex includes coordinates because this is going to be our x-axis. This is going to be our y-axis. And we will have coordinates for that vertex. We will have an x-coordinate and we will have a y-coordinate. And if you remember from our previous discussion in this video, this x value is going to represent a number. The y value is going to represent how high that our bee is flying, which is the same thing as the height. How high is it? And of course, the y is the function value. They're calling the function value f of x. And technically, we could call it the height function because it is going to tell us how high it is. So we could have called it the h function if we wanted to. So I'm going to change it and call it the h function because all of these numbers will be height numbers. They'll tell us how high that b is flying. So that's what we need to find. We need to find the height. We need to find this number right here. But we also have an x value. Well, they tell us here that the x value is the distance along the ground from Sherlock. So this x-axis is going to represent the distance from Sherlock. So that's a distance number. So that is going to be what is the x value is going to represent. It's going to represent some distance. So how are we going to find this height function or this height number? Well, first of all, we're going to find the distance first. We are going to use what I like to call the magic bullet. The magic bullet is this little equation. It's like the x value of the vertex can be found by negative b over 2a. Well, where does the b and the a come from? Well, it comes from the standard form of a quadratic. So standard form of a quadratic equation is ax squared plus bx plus c. And in our function, the b number is going to be in front of the x here at 1.8. So that's going to be is equal to negative b, the b is the 1.8, so negative 1.8, and it's going to be over 2 times the a number. Well, our a number is what's in front of the x squared term, so our a number of our original function is going to be negative 0.03. So negative 0.03. And that is going to give us our x value of our vertex. So we are finding the x value using this magic bullet. Okay, when we crunch that out, that is going to give us on our handy dandy calculator, it is going to give us a value of 30. So the x value of our vertex is going to be 30 inches. That B is going to be 30 inches away from Sherlock when it is at that maximum height. So the 30 is going to be the x value. Okay, so now we still have to find the height number. Well, how can we find the height number? Well, we can take this x value right here, this x value that we just found. We just found 30 inches, and we can plug that back in to our original. So that 30 can be plugged back into our original function. Everywhere there's an x, we are going to put 30. So let's do that. Let's go ahead and plug that in. It's like my y value, which is my function value, which I decided that we were going to call it the h function because that's going to tell us the height. We are going to do negative 0.03 times the 30, and that is going to be squared. And then that's going to be plus 1.8 times 30, and then that's going to be minus 24. So minus 24. Let's kind of scoot all that over a little bit here. Oops. Scoot all that over so we can see it a little bit better here. Okay, so 24. So you see, I took the 30, that was my x value of my vertex, and I put it into my function. So there is 30 everywhere there was an x in my function. I should erase all that so y'all can see that better, right? Okay, so everywhere that there was an x value in my function is where I put the 30 in my function. Okay, when I put that in my handy dandy calculator and crunch all that out, that gives me a y value. My y value of the vertex is equal to 3. So over here, I've got a y value of 3, and that means 3 inches. The B is 3 inches from the ground when he is at this maximum height maximum height of 3 inches, and he is 30 inches from Sherlock at the same time. So 3 inches is the maximum height that the bee reaches as he flies from flower A to flower B. Okay, our next question says, how far away from Sherlock are flowers A and B? So here is flower A, here is flower B, and right there is Sherlock. And remember, this is our x-axis. This is our x-axis, and this whole axis represents the distance. But anytime we have points that are right on the x-axis, remember we call those the x-intercepts. So that point right there and that point right there, both on the x-axis, are referred to as, in math, as x-intercepts. So that is an x-intercept and that is an x-intercept. We can also call them zeros and solutions to our quadratic function. Our number one way of solving quadratics is to try to factor it. But if the numbers are a little wonky, or possibly if it cannot be factored, we will choose to use the quadratic formula. So I think with this one, because our number's negative 0.03, we've got decimal numbers, that's a little bit messy. So very likely this quadratic cannot be factored. So we're just going to use the quadratic formula. So here is the quadratic formula. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. And that will give us both of these x values at these points that are represented by flowers A and B. Okay, so again, we're going to use that ax squared plus bx plus c standard form. So my b number is going to be 1.8. That's going to be my b number. And my a number will be right there. There'll be my a number. And my c number is going to be negative 24. So I'm going to plug all those into the quadratic formula. So negative b means negative 1.8 plus or minus square root of b squared. The b again is 1.8. So it's 1.8 squared, and then minus 4 times the a, which is negative 0.03. That's a 3. And my c is a negative 24. So negative 24. And all of that is over 2 times a again, which is negative 0.03. Okay, and I just keep working it down. So I've got negative 1.8 plus or minus, and when I crunch all of this under that radical, it is going to give me 0.36. 0.36. And then all of that in the denominator, 2 times negative 0.03 is going to be negative 0.06. And then I'm going to crunch that one more time in my calculator, and it's going to give me two different values. There's going to be the value where I add these two things, and there will be the value where I add the two numerator numbers. So my first x is going to be equal to 20, and my second x is going to be equal to 40. So that means that over here on my picture, flower A is going to be sitting 20 inches away from Sherlock, and flower B is going to be sitting 40 inches away from Sherlock. And of course, as it flew from flower A to flower B, it hit its maximum height at 30 inches away from Sherlock. So that is the answer to the question. It's like, how far away is Sherlock from flowers A and B? He is 20 inches away from flower A, and he is 40 inches away from flower B. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.